So this next video is how to use the ideal gas equation, chapter 19. Okay, so this is found in the beginning of chapter 19, pages 375 to 377. So you've got this equation, PV equals nRT, and you're going to use this one over and over and over and over again. P is pressure, V is volume, N is the number of moles, R is the universal gas constant, and T is temperature. Now, unlike Boyle's and Charles and the combined gas law, this one, your volume has to be in liters, okay? All right, your volume must be in liters. Your temperature must be in Kelvin, okay? That's the same as before. Your temperature must be in Kelvin. Your pressure can be in any units, either kPa or ATMs. You just have to make sure that it matches up with your universal gas constant, because R can be two values. Use 8.31 if your pressure is in kPa. You use 0.0821 if your units are in atmospheres. Okay? Now, like I say, you always put units on things because that's how you know things, you're using things correctly, is when all the units cancel correctly. Okay? So let's just start off with one.
You know that chipmunky thingy majiggy? It went up the white thing, which goes all the way up to there. I think it just came out, but I'm not sure.
What volume would 0.245 moles of oxygen gas at 25 degrees Celsius and 65 kPa occupy? Okay. First thing you do, write down all the information you know. This is why we've done this all year long, so that this is nothing new to you. Write down the info you know. 0.245 moles. Write down the temperature, 25 Celsius. Automatically go ahead and convert that into Kelvin. Okay? All temperatures for the gas laws must be in Kelvin. So you automatically add that 273. You read about that extensively in chapter 18 and in the videos. Pressure. All right, what's my pressure? 65 kPa. So if my pressure's in kPa, then I'm going to use that R value, the one that's in kPa's. So 8.31 liters kPa over mole Kelvin, and I'm going to find my volume. All right, so we got our equation, PV equals nRT. If this was a traditional class, it'd be 1 point for writing down the info, 1 point for doing the writing down the equation. And now, through the magic of algebra, we're going to solve for volume.
Dad, is it okay if I play with Cece? Okay. It's okay.
All right, we're having trouble again with getting this thing. All right, see if we can, there we go. So now we have V equals nRT over P. Plug in our volume, or plug in our numbers. We had 0.245 moles times 8.31 liters kPa over moles Kelvin times 298 Kelvin divided by my pressure, which was 65 kPa. And then I look to see if everything cancels correctly. Moles cancels with moles. Kelvin cancels with Kelvin. kPa cancels with kPa. And the only unit that does not cancel is liters, which means the answer must be in liters. So we take 0.245 times 8.31 times 298 divided by 65, and our answer is going to be 9.33 liters. Okay? 3 sig figs. All right? Let's try another one. That one was fun. We should do another. All right. So all of these are going to be ideal gas equations. So how about what is the pressure of 2 moles of argon gas in a 250 milliliter container at 250 degrees Celsius. Okay? So we write down our info. We have 2 moles. We've got a volume of 250 milliliters, but volume must be in liters, so we have to convert. Temperature was 250 Celsius, but we got to convert that to Kelvin, so go ahead and just do those things right away when you're writing down your info. So, and then my pressure is what I'm trying to find. And then let's see, and now my R constant. So my R constant has to be in, well, it could be in either one. They didn't specify. So let's just do it in kPa, okay? So 8.31 liters times kPa over mole Kelvin. Here's my equation. Now let's solve for pressure. Doing this problem reminds me of when I was in Guatemala and I was chased by wild dogs. You had to always carry rocks on you because you'd stop and pretend that you're going to throw a rock right at that dog. Then the dogs thought twice about trying to bite you. Now you may ask, what has this to do at all with chemistry? Well, it actually doesn't. I just think I might put this question on our next quiz, just so I know that you watched this video. All right, temperature. All right, volume is 0.250 liters. Calculate the pressure. And we get a very high pressure. Oops. Okay. So that's how you do it if you were solving for pressure. Let's just do one more. Let's just calculate, let's do temperature. what is the temperature of a gas, or let's say of 0.782 moles of helium gas at a pressure of 2 atmospheres and a volume of 24.0 cubic centimeters. Okay. Well, our volume is 24 cubic centimeters. Our pressure is 2 atmospheres. Our moles is 0.782 moles, and because our pressure is in atmospheres, we're going to have to use the R value in atmospheres. Okay, we're going to find our temperature. Oh, volume has to be in liters, so we have to convert that. 1,000 cubic centimeters is 1 liter. Okay. Okay. So now we can take our equation, solve for temperature. So let's see here. We're going to have our pressure was 2 atmospheres times our volume divided by the R value and then multiply that by what do we multiply that by? Oh, the number of moles, which in this case was 0.782. And then we get our temperature. Units. ATMs cancels with ATMs. Liters cancels with liters. Moles cancels with moles. The only unit left is Kelvin. So whatever our temperature is, it's going to be in Kelvin. So this temperature is going to be pretty darn cold because I came up with a temperature of 0.0747 Kelvin. So if we wanted to convert that to Celsius, you would subtract 273. So that means negative 272 degrees Kelvin. Now, you know from reading Charles' law, the coldest you can get, in other words, absolute zero, is negative 273 Celsius, or 0 Kelvin. So we are almost, in this problem, at the coldest you can be. We're at negative 272. Okay? And the last thing I'm just going to point out, and then I'll stop the video, is that nowhere in the problem does it matter that it's what type of gas it is. I think I said it was like argon gas. In all of these problems, okay, the type of gas, argon gas, oxygen gas, nowhere in the problem does that come into play. Why? Because we get to use the ideal gas equation. Nowhere in this equation does it say that you have to take into account the type of gas. If we use the real gas equation, then we'd have to know how big oxygen gas was and argon gas was. We'd have to know how attractive those gases were. So be thankful that we don't have to use this equation, and we just get to use the ideal gas equation. All right, until next time.